Okay, let's look at the calculator section of this test. Question 5. Three friends with jobs in different companies are chatting one day about which one of them is more important for their company. They decide to settle the discussion by working out who gets paid the most relative to all the other workers in their workplace. They draw up the following table. Who gets paid the most relative to the other workers at their workplace? Okay, so this is a question about comparing scores, and if we remember the statistical tool that we have to compare scores is using standard scores or z-scores. So we have this formula. My z-score is my raw score minus the mean divided by the standard deviation. So in order to compare these scores to work out who gets paid the most, we're going to need to convert them all to z-scores. So we've got Andrew, Beatrice, and Klaus. So for Andrew's z-score, I'll label that AZ, equals his raw score, which is 83,000, minus the mean, 78,000, divided by the standard deviation, 4,500. Beatrice's score is going to follow the same pattern, 104,000 minus 130,000 divided by 13,000. And Klaus is going to get 205,010 minus 193,600 divided by 18,000. I'm going to put each of those into my calculator. So let's start with Andrew. $83 minus 78,000 divided by 4,500 is going to give Andrew a z-score of 1.1. Beatrice is going to get 104,000 minus 13,000 divided by 13,000. No, I've put a number in wrong there. I've written 13,000, that should be 130,000, and that gives Beatrice a z-score of -2, and Klaus is going to get 205,010 minus 193,600 divided by 18,000, which gives him a z-score of 0.63. Okay, looking at these z-scores we've got now, we can answer the question, who gets paid the most relative to the other workers at their workplace? Andrew gets paid the most. Relative to the workers at his workplace. And the interesting thing there is to look at his raw score was actually the lowest, so he's getting paid the least, but by converting to z-scores, we can see that he is getting paid the most relative to the other workers at his workplace, which is what they were arguing about. Okay, let's move on to question 6. 2 different machines are used to produce rubber balls. 30 balls are picked randomly from each machine, and their weights were recorded in the frequency table below. Okay, so we've got weights in intervals, and the frequency table for machine 1 and machine 2. Question A, which machine produces heavier balls? Justify your answer. So we're going to need to work out an average that's going to be able to help us answer this question. So for that, I'm going to put that data into my ClassPad. So here we go. Hopefully you can see the screen all right here. I'm going to go to menu. We're going to go statistics. And I've already got a bit of data in there. It's not the data that we need, so I'm going to clear that all. All right, in order to put this into the class pad, I first need to work out the midpoint for each one of these weights. So I'm just going to write those next to them over here. So 12.5 to 12.9. If I add those together and divide them by 2, I'm going to get a midpoint of 12.7. This will be 13.2, 13.7, 14.2, 14.7, 15.2, and 15.7. Let's put that data into my class pad now. So we've got 12.7, 13.2, 13.7, 14.2, 14.7, 15.2, and 15.7. Okay, in list 2, I'm going to put the frequencies of machine 1, which are 1, 2, 7, 10, 8, 2, and 0. And in list 3, I'm going to put the frequencies for machine 2. So that'll be 4, 9, 9, 4, 2, 0, 0. Okay, now I'm going to work out the mean of each one of those so that I can compare them to answer question A. So first let's work out the mean of machine 1. So the mean of machine 1. And I'm just to save myself some time, I'm going to read ahead to the next question, question B, which machine is more consistent? Justify your answer. Consistency is about which machine produces, if it's more consistent, it means that there is less range of scores. So to work that out, I'm going to need the standard deviation, and whichever machine has the lower standard deviation will be more consistent. So while I'm calculating the mean, I may as well also calculate the standard deviations for machines 1 and 2 to save myself a bit of time, just reading ahead there. Okay, let's first do machine 1. So I've got calc 1 variable, my X list is list 1, and my frequency is in list 2. That gives me a mean of 14.17, and it gives me a standard deviation of 0.58. Let's do the same for machine 2. Calc 1 variable, X list is list 1, frequency is now list 3 because that's where I put my frequencies for machine 2, and I get that there is a mean of 13.54 and that there is a standard deviation of 0.55. That means we can answer this question now. Which machine produces heavier balls? That would be machine 1 because it has a higher mean. And which machine is more consistent? That would be machine 2 because it has a lower standard deviation. Okay, moving on to the next page. Question 7. An applications test has a mean of 50 and a standard deviation of 6. If a student's standard score is 1.5, what was their raw mark? Okay, that's going to require us to work backwards a little bit. So first I'm going to write down the formula for standard score that we know. So my z-score equals raw minus mean over standard deviation. Now let's put in the numbers that we have here. So I have that the z-score is 1.5 and that equals the raw mark, which we don't know yet, so I'm just going to leave it as an R, minus the mean, which we have is 50, divided by the standard deviation, which was 6. I'm going to rearrange this formula to get to isolate R. So first I'm going to move that 6 over to the other side and get that R minus 50 equals 6 times 1.5. And therefore R equals 6 times 1.5 plus 50. So I've taken that 50 and moved it to the other side. Let's get my calculator back and let's work out what the answer to that will be. So I've got 6 times 1.5 plus 50. The raw mark was a mark of 59. I can also, maybe just to check or to save time, instead of rearranging that formula, I could have done the same thing by doing this. I could have gone action, calculation, sorry, not calculation. I'm doing the wrong thing there. I want to go, let's do it like this. Let's get my keyboard up and let's go solve. And I'm going to use X here instead of R, and I'm going to say 1.5 equals X minus 50 divided by 6. And I'm going to let it solve it for me and get X equals 59. Question 8. Waste physics scores are normally distributed with a mean of 60 and a standard deviation of 15. Question A, a student is chosen at random. What is the probability that they have scored more than 70? So to put this into the notation that we've been using, I have that X is normally distributed with a mean of 60 and a standard deviation of 15. And I'm looking for the probability that someone has scored more than 70, that X is greater than 70. And for that, I'm just going to plug it into my calculator. You'll notice this question is only worth 1 mark because it just involves putting something straight into the calculator. So we'll go calc, distribution, normal CD. My lower limit is 70. My upper limit here is actually going to be 100 because you can't get higher than that, although I could have done infinity there as well to put the absolute upper limit, but just for it to make sense in the context of this question. My standard deviation was 15 and my mean was 60. And the probability is 0.25. Let's just check quickly what difference it would have made if I had put infinity there instead of 100. And it's still 0.25. And that makes sense because getting higher than 100, even if you could, is so high above the mean that it's going to make very little difference to the probability of getting it. And we only really need to give our answers to 2 decimal places. So 0.25 is fine there. Question B. 80% of scores will lie within X marks of the mean. Determine X. So let's just draw this distribution so I can give you an idea of what we're talking about. This is the mean, 60, and 80% of marks lie within a certain number of the mean. So that means we're talking about an area around the mean, where within this area, 80% of the scores lie. We want to know what these numbers are. So let's go back here, and it means we're going to need to do an inverse distribution. So we want inverse normal CD. My tail setting is center, because I'm centered around the mean here. I'm not looking for an area off to the right or to the left. My probability is 0.8, because I was looking for 80%. Standard deviation of 15 and mean of 60. And I get that my 2 marks here are 40.8 and 79.2. So what that means is that this one is 40.8 and here is 79.2. So if it's within X marks of the mean, then we're only looking for the distance between the mean and this mark, or the mean and this mark. They should be the same. And so X equals 19.2. X equals 19.2 because within 19.2 marks of the mean on either side, that's where 80% of the scores will lie. Question C. What mark would you need to get to be in the 95th percentile? So just remember what a percentile means. If we're in the 95th percentile, it means that 95% of the scores are below our score. So if we draw our bell curve, we're looking for a score over here where this red shaded area contains 95% of the scores, and we want to know what is that mark over there. So again, we're going to need to do an inverse distribution, except here we're looking for the area off to the left. We want a probability of 0.95, and we get that the score would be a score of 84.67. Okay, 300 students are chosen at random. Estimate how many of these students scored less than 50. So this is a two-step process. First, we need to know what percentage of students would score less than 50. So for that, I'm going to go back to my distribution. Not interval, I want distribution, normal CD. And I'm going to say if I've got a standard deviation of 15 and a mean of 60, what percentage of students would score less than 50? So I'm going to put my lower as 0 just because it's a test and you can't get less than 0, but you could do it as negative infinity and it wouldn't make a huge difference. And I'm going to get that my probability equals 0.252. If I have 300 students, then the probability of 0.252 means that of those 300 students, the number of them that get less than 50 will be 300 times 0.252. This is one of those situations where it would be good to have two calculators, the big ClassPad and the scientific one, to do these smaller things on the scientific calculator while you're using the statistics function of the big one. But I have to jump between the different functions of the ClassPad here. 300 times 0.252 gives me 75.6. We obviously can't have 0.6 of a person, so I'm going to round that to approximately 76 people. Last question here, question E. If all 300 students were ranked from highest to lowest, approximately what mark would you expect the 220th student to get? Okay, so here again, it's one of those inverse ones. So first, I'm going to convert the number 220. I'm going to convert that to a percentage. So what percentage of students has that 220th student got above or below? So if we have 300 students in total, the 220th student has beaten 80 students. So what percentage would that be? It'll be 80 out of 300. Which is 0.267 or 26.7%. So that 220th student has beaten 26.7% of the 300 students. So if this is my distribution, and this here is my 220th student, then the red area off to the right, off to the left here, that I am going to shade contains 26.7% of the students. So for that, we're going to need an inverse distribution. So I'm going to jump back into my statistics function, inverse normal CD. The tail setting I've got in that diagram there is off to the left. The probability is 0.2667. The standard deviation still was 15 and the mean was 60. And it's going to tell me that my score there is 50.66. So I can expect that 220th student to get a score of approximately 50.66. And there you go. That's the test done. Let me know if you have any questions.